Alright guys, we want to check out, kind of extend what we've been talking about over the last couple days and just check out what's going on with some other angles. We've talked about the central angle, and that's just an angle that has a vertex at the center of the circle. So what I've drawn on here is just a central angle with a measure of 45 degrees. And we know, based on what we've talked about, that the arc that is intercepted by that central angle, or the arc that that central angle projects to, as I say kind of informally, is going to be equivalent, is going to have the same degree measure as the central angle. Alright, so what I want to do is we're going to take this and change it just a little bit. So I want to take this central angle, and what I'm going to do is change the location of the vertex, but notice I'm not going to change the angle measure. Alright, so we started with a 45 degree angle. I'm not going to change that angle measure. I'm just going to kind of drag this to the left so that the vertex is now actually on the circle. Okay, so we changed it by dragging the vertex. Again, we didn't change the angle measure. We just took that angle, and instead of having its vertex on the center of the circle, it's now on the actual circle, on the outside of the circle. It's one of the points that make up the circle. Okay, first and foremost, this is now not a central angle, obviously. Its vertex is not on the center. It's not a central angle. It's what we call an inscribed angle. Okay, so an inscribed angle is an angle whose vertex is on the circle. Alright, and then there's some other stuff. It has some sides that are made up of chords on the circle. So this chord EG would make up the side of this angle. ED would make up the other side of this angle, and so on. But most importantly, we've got angle GED is an inscribed angle. So what we want to look at is what happens to the arc that it projects to, or the arc that is intercepted by this inscribed angle. You can see the central angle, we talked about it before, projects to an arc that has the same degree measure. But what happens when we take that vertex and drag it out is we increase the degree measure of that arc. We increase the degree or the measure of that arc. And so you can kind of tell what's going on here a little bit. If I take the intersection of this angle here and drop it straight down, let me try that again. So I want to take this intersection right here and drop it straight down so that it's going to hit my center. Well, if this is a vertical line and this is a horizontal line, then our central angle is now a 90-degree angle, and that arc that it projects to has also got to be 90 degrees. So what happens is we create this this interception of the arc, and the arc that's intercepted by this inscribed angle is now larger in comparison to the arc that's intercepted by an angle of comparable degree that's a central angle. All right. The point in all of this is you look at the angle measure of the inscribed angle and the arc that it projects to, and it's going to be bigger. It's going to be bigger than if that were a central angle. And in particular, you can tell I dropped this line straight down. That's a vertical line. This is a horizontal line. So this measure is actually going to be 90 degrees. That's the measure of the intercepted arc. So the relationship between the inscribed angle and the arc that it projects to, the arc is actually double the measure of the inscribed angle. I've got a little applet here that hopefully will allow you to see what's going on with this. And this is the same exact scenario that we talked about before. What you can see is that the arc here in this little applet that's subtended has the same endpoints for the inscribed angle as it does the central angle. So what we're going to do is we're just going to drag this vertex around. You can see my central angle is 90 degrees, which means my arc length is 90 degrees. But my inscribed angle that projects to those same two endpoints that creates that arc is half that measure. And it doesn't matter if we have this scenario where we just extend it to one side horizontally, or if we have some some other inscribed measure, you can see I'm just kind of swinging this vertex around. If it projects to the same endpoints and it projects to an arc with measure of 90 degrees, then that inscribed angle's got to be 45 degrees. Doesn't matter where it is on the circle, we can move it over here to where it's almost touching there, and it's going to stay 45 degrees. Okay? If we change the central angle, we're going to change this measure. We're going to shrink that down a little bit, subsequently changing the arc measure because these are directly correlated here. So my central angle, I'm going to change, let's drop that down to, let's say, 34 degrees. Oh, 32, sorry. 32 degrees. Then we know that the arc that central angle projects to, the measure of that arc, is going to have the same measure, 32 degrees. But look what happened to my inscribed angle. My inscribed angle shrinks by half. All right, and again, it doesn't matter where we put this thing, where we put the vertex of this inscribed angle. If it projects to the same endpoints that create the arc as the central angle, then it's going to be half the measure. All right. All right, so let's just kind of put into math terms what we just talked about here. What we talked about essentially was the theorem that describes the relationship between the inscribed angle and the intercepted arc. The measure of an inscribed angle is half the measure of its intercepted arc. Okay? Oops. Half the measure of its intercepted arc. All right, so to put into math terms what we just talked about, if we, let's say, we're going to put our vertex here on E, and we're going to create an inscribed angle that has endpoints on the circle. So what I know about this is that this angle right here, the measure of angle GED, is going to be equal to 1/2 the measure of the arc that it projects to. So one-half the measure of arc GD, because GD are the endpoints of this particular thing, and it projects to, here's my endpoint G, it projects to this arc that I'm kind of tracing out right here. And I missed a little bit, but hopefully you guys kind of get the picture. So there's the arc that inscribed angle projects to. And because that's the arc that it projects to, we know that the inscribed angle is 1/2 the measure of the arc. All right, similarly, if I draw this other inscribed angle measure, or this other inscribed angle, then I know that that relationship exists, that relationship that the inscribed angle, measure of angle FED, is going to be equal to 1/2 whatever the measure of FD is, arc FD. And again, one last time, we know this because this is the arc that's intercepted. That's the arc that's intercepted by this particular angle. And the green arc right there is the arc that is intercepted by this particular angle. Alright, so a couple quick properties that we want to look at of these inscribed angles, and I'll do this very quickly. Hopefully this is relatively intuitive for you guys. We're looking at measure DGF, and this is an inscribed angle because it has a vertex on this thing. And we notice that that inscribed angle projects to this arc DF. Okay, so let's just go ahead and trace that. So there's arc DF, and we know the relationship between this inscribed angle right here. This angle measure is going to be half the measure of whatever arc DF is. All right, but we also have this other inscribed angle, arc DEF, right here, and it happens to project to the same arc. And so we can check out, again, we can trace using those endpoints. Here are my endpoints for both of these particular inscribed angles. And so if inscribed angles have the same endpoint and essentially project to the same arc, And what do we know about them? We know that they have to have the same measure. All right, so it would have to be that this guy right here, DEF, has to have the same measure as DGF. All right, and that's all this is saying up here. If inscribed angles of a circle intercept the same arc or are subtended by the same chord, then the angles are congruent.
Daddy?
All right, so the relationship that we can write here, because these two inscribed angles project to the same arc, we know that the measure of angle DGF is equal to the measure of angle DEF. So if the inscribed angles project to the same arc, they've got to be the same angle measure. All right, guys, the next property that we want to look at is what happens if we have an inscribed angle that projects to a semicircle, or in other words, this inscribed angle has endpoints that create a diameter of the circle. All right, and there are a bunch of different ones that you can draw. So this one in particular has endpoints that create a diameter. This guy right here, if we were to draw another, has endpoints that create a diameter. What we just looked at is, hey, both of these project to the same endpoints and project to this arc right here, which happens to be half the measure of the circle, which we know is 180 degrees. Well, what do we know about those things? These angles actually have to be 90-degree angles. The inscribed angle is half the measure of the arc that it projects to. So if the arc is half the circle, that's 180 degrees. We project that back to our inscribed angles. Those are half that measure, and so they must be 90-degree angles. Okay? Must be 90-degree angles. So this would have to be a right angle, right angle.